Hey, what is up everyone? I hope all of you are doing great. In today's question, we have bottom arm of a U-tube of uniform cross section has length L and vertical arms each of length 3L. Okay. The tube is held with its parallel arms vertical and filled with a liquid of density rho to occupy a total length of 4L. So the length of the total liquid is 4L, and then it is made to accelerate horizontally in the plane of the tube with an acceleration g. What will gauge pressure at the midpoint of the bottom arm be immediately after acceleration of the tube is made abruptly 0? Okay, so we need to find out the gauge pressure at the midpoint of the liquid just after the tube stops accelerating. Fine. So this is the structure of the liquid and the tube. The whole assembly is moving towards left with an acceleration g, and due to that both the liquid columns in the left and right hand side won't be equal. So of course the liquid column on the right hand side will rise by some amount. Okay, and let us consider that the length of the left column of the liquid is x, so the length of the right column of the liquid would be 3L minus x, because total length is 4L, this is x, then this is L, so this should be 3L minus x. Okay, so pressure at P naught, at this point is P naught, that is the atmospheric pressure. If we come downward, the increase in pressure would be by an amount of rho gx, so P naught plus rho gx is the pressure at this corner. If we go along this line, we are going against this acceleration, so it gives rise to an additional amount of pressure, that is rho gl. Okay, and if we now rise upwards, there will be an increase in pressure. So initially it was this one, so P naught plus rho gx plus rho gl minus rho g 3L minus x. Okay, and this whole pressure should be equal to P naught. Okay, so P naught plus rho gx plus rho gl minus rho g 3L minus x equals to P naught. Sorry, equating this whole equation, okay, solving this whole equation, you will get x equals to L. Okay, so this length is L, 2L. Okay, so finally we got the length of both the columns. Now we need to find out the gauge pressure at the midpoint, that is the pressure difference and the absolute pressure here subtracted by the atmospheric pressure. Okay, now one thing before solving that one, we need to discuss first, can we apply Bernoulli's theorem here? First of all, energy is conserved, no doubt, because there is no friction at all, but Bernoulli's theorem won't be applied in this situation because the motion of the fluid is not steady at all. Okay, so Bernoulli's theorem is not valid here. Okay, so just when the liquid when the tube stops accelerating, so the acceleration becomes 0 due to the weight or the imbalance of the weight due to the two columns on the right and the left will create an acceleration on the whole liquid column. So the net force acting on the whole liquid column would be due to this vertical heights. So the net force due to the right column and the left column would be 2L cross sectional area A rho g, okay, subtracted by L cross sectional area A rho times g. So the net force acting on the whole liquid body is this one, and this will create an acceleration A, suppose, and the mass of the whole liquid body is rho times the total length, that is 4A times the cross sectional area. So that would give rise to a net acceleration of g by 4 just after the tube stops accelerating, right? So this acceleration is of the liquid. Initially the acceleration was of the whole assembly, which was moving in the horizontal direction. Now for finding out the gauge pressure at the midpoint, we will just take a portion of the liquid. Okay, so we will take just this portion of the liquid and we will draw the free body diagram of that portion. Okay, so atmospheric pressure is acting here, absolute pressure at the midpoint is P1. Okay, weight of the liquid of this vertical column is W, and the resultant acceleration is g by 4, and it is in the upward direction. I mean, for the horizontal liquid it is towards left, and the vertical liquid it would be in the upward direction. So the net force is towards in this manner. So P1 times A minus the weight of the vertical liquid, that is rho LA times G minus force due to this atmospheric pressure. This will be equal to the mass of this L-shaped liquid, that is rho L plus L by 2 times A times the acceleration, which we already have calculated, that is g by 4. Now just reassemble all the variables. If you find out P1 minus P0, that is the gauge pressure, it would give you 11 by 8 rho GL, that is 1.375 rho GL. So I think option D is the correct answer. So I hope you all have found this video helpful and informative. If you are new to this channel, please do subscribe, and if you want this kind of videos to pop up in your recommendations, just click that like button and share it with your friends, and I'll see you in the next one. Peace, take care.